Hello and welcome to this video on finding a basis for a subspace defined by an equation. So this video is just going to be up of a few examples. It should be a shorter video where I'm just going to go over several examples of I'm going to be given a subspace of some Euclidean space, whether it be R2 or R3. I'm going to be given a subspace of that Euclidean space, and then I wish to find a basis for that subspace, right? So that means I want to find a set of vectors in that subspace that spans the space, and also a set of linearly independent vectors. Right. So let's get started. So my first example, and this is the same instruction for every example for the rest of the video. I'm asked to find a basis for each subspace, right? So I'm already telling you this is a subspace. You can check it on your own. You can see that it's non-empty. It's closed under vector addition. It'll be closed under scalar multiplication, right? And it's a subset of R2, so it inherits all those other 8, vector space axioms. So this is a vector space, a subspace of R2. Again, I'm not going into that. You check that on your own. So again, what we're trying to do here is find a basis, right? So in other words, as I said out loud earlier, we're trying to find a set of vectors that is linearly independent linearly, that's an L, sorry, that is linearly independent and spans S. Right, I'm assuming you know what these mean, right? If a set of vectors is linearly independent, it means that none of the vectors in the set can be written as linear combinations of other vectors in the set. And when I say a set of vectors spans S, that means that every vector in S will be able to be written as a linear combination of the vectors in this set we're trying to find. Right? Okay. So, and then the title of this video was find a basis for a subspace defined by an equation. So in each of these examples, we're going to have S equals some set of vectors such that their components satisfy some equation, right? They'll be after the bar, some equation that the components of the vectors in S will satisfy. All right. So S in this case is made up of all the vectors from R2 such that -3 times the first component plus the second component will be equal to 0. Now another way to put this, you could solve for one of these variables. Y would be easy to solve for. Another way to put that, instead of saying that -3 times the first component plus the second component must be equal to 0, if I were to solve this for y, we'd have y would be equal to 3x. Right? So another condition, so that every vector in this set, the second component is 3 times the first component. All right, so let's describe that out. Right, I'm going to write that out. Each vector in S, right, every single vector in S will look like this. And you have a first component x, a second component y. These are real numbers. But by the condition that needs to be satisfied, this second component is 3 times the first component. So you see the second component is 3 times the first component. So x and then y equals 3x, where x is a real number, x is a scalar. And do you see how both of these have, this scalar of x in common? I can pull that out and say every vector in S is a scalar multiple of the vector 1, 3. Right, and I'll write that out in words. Okay. So this line right here is telling me that every vector in S is a scalar multiple of the vector 1, 3. Well, if we have a set of vectors that, all the vectors are a scalar multiple of one vector, that means that that vector, the set with just that vector would span this set. Or in other words, in other notation, we could say that, therefore, S is equal to the span of the set with just the vector 1, 3 in it. Right? Because remember what this means. This means that if S is the span of 1, 3, means that every vector in S is a linear combination of the vector 1, 3. Well, a linear combination of a single vector is a scalar multiple. All right, so we've got the set with vector 1, 3 in it spans S. All these mean the same thing. This statement here, this little line, this equation here, this statement here, all of them mean the same thing. So that's part one of finding a basis. I found a set of vectors that spans S, right? The set of just the vector 1, 3. Then the next question is this set of vectors linearly independent? Well, it's only a set of one vector, and I've talked about linear independence and dependence in plenty of other videos, so you can check those out if you wish or read up on it. But a set with just one non-zero vector like this has is linearly independent. All right. So not only does this set span our subspace S, but this set with the vector 1, 3 in it is also, linearly independent. Now you can go through and do the formal check where you, take a scalar multiple of this and set it equal to the 0 vector and figure out, oh hey, that only has the trivial solution. Therefore, this set is linearly independent. You can do all that if you wish, but so check on that. Check on that. Therefore, this set with just the vector 1, 3 in it is a basis for this set of vectors S that's described up here. All right. So therefore, the set with vector 1, 3 is a basis for S. Right, that vector, a subspace is a vector space. This vector space S has a basis of 1, 3. Right, great, and that's really what these boil down to. So you see what I did in this, when I looked at this a subspace that's defined by an equation. I solved the equation for one variable. So y equals 3x, and in this equation, x would be considered like a free variable. I can pick whatever value for x I want, and then y has to be fixed. Right? So if you solve for a variable, the number of variables it depends on, those are the free variables. And what you're going to notice is that the basis will have the same number of vectors as the number of variables that are considered, free on the other side of the equation. When you solve for one of the particular variables, you'll see what I mean in the second, in the third example I've got here as well. All right. All right. So here's another one. Now this time I have a subspace of R3. Right, so S equals this set of vectors, three components. The first component is some number x, the second component is some number y, the third component is always 0. Right? And then there's also this condition, this equation that is satisfied by the components. It says that the second component must be equal to the first component, right? So the vector, 1, 1, 0 would be an S, 2, 2, 0 would be an S, negative 1, negative 1, 0. Whatever. As long as x and y are the same, the first and second component are the same, and the third component is 0, you have a vector in S. Now again, we're trying to find a basis for S, and I'll write that again. Find a basis for the vector space S. Right, so a set of vectors that spans S, right? That means that every vector in S is a linear combination of the set of vectors we find. And also, the set of vectors is linearly independent. Alright, so just as last time, I'm going to take a look at, well, okay, what do these vectors in S look like, right? Every vector in this vector space S, this subspace S, looks like this. You have a first component x, a second component y, and a third component 0. And this is already solved for. Y equals x. And again, if you think about it, y is solved for, x is solved for as well. Doesn't matter. You could think of x as the free variable, or you could think of y as the free variable. I can pick anything. I'll say let's think of x as the free variable. I can pick whatever I want for x. But when I do, then y has to be fixed. If I pick 7 for x, then I can't pick whatever I want for y. Y has to be 7, and so on. So there's only one free variable. So you're going to see there's going to be just one vector in our basis later. But let's see that. So every vector in S looks like this, but we have the condition that y is equal to x. So I'm going to replace y with x here. So first component x, second component x, and third component always 0. And then just as in the example before, every single one of these components has a factor of x. A scalar multiple is a scalar multiple is a multiple of x. Right? So I can pull that scalar of x out, and we have x times the vector 1, 1, 0. Right? So what we're seeing here is that every vector of S, right, each vector of S is a scalar multiple of the vector 1, 1, 0. So another way of saying that is that S, this vector space, this subspace of R3 called S here, is equal to the span of the set with just the vector 1, 1, 0 in it. Or you could say that the set with 1, 1, 0 in it spans S, right? And that's, one thing you need to look out for when you're trying to find a basis, right? I have found a set of vectors, just one vector, that spans S, right? Every vector in S is a linear combination, or a scalar multiple in this case, because there's only one vector, of 1, 1, 0. And then without bringing up another page, I'm just going to do this over here. And just as in the last example, this is a set with a single non-zero vector, so it is linearly independent. Again, you can check that formally if you wish. I'll just say is independent, right? Just no, I mean linearly independent. Wonderful. So this set with, I guess I will bring a new page because I don't have any more room to write. So this set with the vector 1, 1, 0 in it is a basis for that vector space S, that subspace of R3 called S. Great. All right, I'll put it in a box, right? That's my answer. All right. So again, notice when I have this vector space, defined by an equation, I solve for one of the variables, and then the number of variables on the other side will be the number of free variables, will also be the number of vectors in my basis. As you notice, this had one variable that I called free. The first example had one variable that I called free. And each one of these first two examples had a set of vectors with only a set of one vector as a basis. Alright, and finally, this is the last example. Like I said, it's going to be a shorter video than you're probably used to from me. So here's another set, another vector space, a subspace of R3. Right? So S is the set of vectors that look like this, where you have the first component X, second component is the number Y, third component is Z, such that -2 times the first component plus the second component minus the third component is equal to 0. Alright, and you can play around and figure out what values of X, Y, and Z would make this a true statement. To figure out some vectors of S. But again, what we're trying to do here is find a basis for S. Right. So as I did before, looking at this equation here, this equation is equivalent to the following. I can solve this for one of the variables. So saying that -2 times X plus Y minus Z equals 0, that's the same thing as saying it'd be easy to solve for Y here because it's already got +1 as a coefficient. So Y equals, and then adding 2x, adding Z, 2x plus Z. Alright, so you see here I have 2 free variables this time. Two variables that I could say are any value I wish. I could let X be 100 and Z be -5. But if I do that, then Y would have to be 195. Y can't be anything I want. But these two can. And what we're going to see is that the number of free variables in the equation that describes the vector space, the subspace, is going to be the number of vectors in a basis for that subspace. Okay, and then as with the others, all right, let's take a look at what does every vector in S look like. Every vector in S looks like the following. You have a first component X, second component Y, third component Z, but we said that it has to satisfy this. Y has to be equal to 2 times the first component plus the third component. So I'll replace Y with that. So you have X, and replacing Y with 2x plus Z, and then Z is still Z. Alright, so instead of having a scalar multiple of one vector, what we're going to see here is we're going to have a linear combination of 2 vectors. Right? I mentioned the number of free variables will correspond to the number of vectors in a basis. So I'm going to split this up into the sum of 2 vectors, one involving the X terms and one involving the Z terms. So this vector here with the X, 2x plus Z, and Z components is the sum of the vectors with X terms, X, 2x, and 0, Right? There is no z in the third component. Plus the vector, with all the elements being, all the entries being, all the components being z terms. There's no z term in the first component, right? 0, and then z, right? And do you see how, like, this first vector here, and you can see that the sum of these would indeed be this, right? The first vector, I can factor out that scalar of x. I have x times, 1, 2, 0, plus, and then the second vector here, I can factor out the scalar of z times 0, 1, 1. Right. And so look, all right, this is a scalar times this vector plus a scalar times this vector. This is a linear combination of these two vectors. So what we are seeing here is that every vector in S, right, each vector in S is a linear combination of these two vectors of 1, 2, 0 and 0, 1, 1. Well, great. So we would say that S is equal to the span of those two vectors, right? The span of the set with these two vectors in it. Oops, 0, 1, 1. Right, 0, 1, 1. All right, or in other words, you could say that this set with 1, 2, 0 and vector 0, 1, 1 spans S. Right, every vector in S is a linear combination of these two. So that's, step 1 to showing a basis. And step 2 was to show that, this set of vectors is linearly independent. Now, again, I put up other videos on this. This is a set of only two vectors, and these two vectors are not scalar multiples of one another. They don't depend on one another. Right? I can't multiply this vector by any scalar to get that one, and vice versa. So if that's the case, right, when you have a set with two vectors, you can very easily tell if it's a linearly independent set or not. These are not scalar multiples, so this set with 1, 2, 0 and 0, 1, 1, this set is linearly independent, or again, I'll just say independent. Now, if you I'll make a little warning here, right, just because people tend to make mistakes very often when they only see a few examples. All these examples I've done in this video so far, you've had a set with one vector or two vectors. If you have a set with a single vector or a set with only two vectors, it is very easy to tell. You can do a little quick shortcut look at it. It's very easy to tell if the set is linearly independent. However, when you have a set of three or more vectors, right, three or more, you might have to actually set up that equation where you take a linear combination of those vectors, set it equal to the 0 vector, and figure out if it has only the trivial solution or not. You may be able to see it. You might see that one vector is a linear combination of others and that they're dependent. But when you have three or more vectors, you're going to have to do more checking. Right? You're going to have to do more work, more thinking. Right? It's just these sets with 1 and 2 vectors. I just wanted some quick examples here. So great. This set is therefore a basis for this vector space S, right? This subspace of R3 called S. So the set with, vector 1, 2, 1, gosh, gosh. 1, 2, 0. That is a 1. Sorry, just a very thick 1. And then 0, 1, 1 is a basis for S, right? So that means, again, every vector in S can be written as a linear combination of these two, and these two vectors are linearly independent. Wonderful. All right. So that's it for this set of examples. Again, there are plenty of others I could have made up out there, where it's you have a subspace that relies on the solutions of an equation. So again, I would say solve that particular equation for one variable, and then the number of variables on the other side will be free, and that number of variables will end up being the number of vectors in your basis. Okay. I guess if there are the same number of variables as there are components. All right. I guess if there was another variable tacked on, it would be different. But general guideline for right now, I mean, there's only going to be 3. There should only be the same number of variables as components, or fewer, right? Because how would another variable be added on if there's only so many components? If there's n components, how could there be n plus 1 variables? All right, so the number of variables in the equation should be, equal to the number of components or less than the number of components, right? And you saw that in the, I could have had here, instead of negative 2x plus y minus z equals 0, I could have just had negative 2x plus y equals 0, right? And done that. But then z would also be free, right? You could let z be whatever you wanted. So there'd still be the same number of free variables. Okay. But yeah, just follow that procedure. Solve the equation for a variable, and then replace it, and look at what every vector in the set looks like, and try to write it as either a scalar multiple of a vector or a linear combination of several vectors, so you get a set of vectors that spans the space. And then you have to check, is that set of vectors that spans the space linearly independent? And if it is, great, then you have a basis. If not, then you can remove a vector, or just reduce it to a set that is linearly independent, and you've got your basis. Great. All right. Have fun practicing problems like this, and thank you very, very much for watching.